Sorry, due to some reason, the video was interrupted in between. So this is the continuation from the previous video. Um, we were talking about the complex reaction, and we saw that this reaction complete in several steps. And for determining the rate of the reaction, we have to look for the slowest step, because the slowest step determines the rate of the reaction. And next is for writing rate law. If we have to write rate law for the complex reaction, then once again we have to go towards the slowest step. And in this slowest step, we will write uh, the rate law, meaning simply the slowest step would help us to write the rate law. The concentration of the reactant present in the slowest step will be used for writing the rate law for any complex reaction. Now some of the example of this complex reaction is, number one is oxidation of ethane to give carbon dioxide and water. Oxidation of ethane to give CO2 and H2O. Here there are consecutive reaction present, which is involved for the completion of oxidation of ethane to form CO2 and H2O. Another example for this complex reaction is 2NO2Cl giving 2NO2 plus Cl2. This is an equation of a complex reaction. Uh, Experimentally, the rate law which is for this reaction is experimentally determined rate law for this reaction is K, concentration of NO2Cl power 1. Now, since it is a complex reaction, it has simple steps, and that simple steps is the mechanism of this reaction. So what are those steps in which this reaction is completed? So firstly, the first step is this NO2Cl splits to give NO2 plus Cl, chlorine. This After this steps, NO the remaining Na2Cl combines with this chlorine and give again NO2 plus Cl2. This Cl goes with the Cl and forms Cl2. These two steps are needed for completion of this complex reaction. So this two is called as the mechanism of the reaction. This reaction has two steps, and these two steps are the mechanism for this reaction. Among these two steps, this is the slow step and this one is the fast step. This step, which is to the slow one, this is very useful because I have written earlier that the slow step will help in determining the rate of the reaction, and also we will write the rate law with the help of the slow step only. And if we will use this step to write the rate law, then rate law will be like this: K, concentration of product NO2Cl, and we can see that the power is 1 over here. So this rate law is as same as which was determined experimentally. So this is another example for the complex reaction, and this is the mechanism, and this is rate law equation which is made with the help of this slow step. Going toward the one more example of this complex reaction. One more example of this complex reaction. 2NO combining with 2H2 giving in product N2 plus 2H2O. This is a complex reaction which I have written: 2NO combining with 2H2 giving in product N2 plus 2H2O. Now, since it is a complex reaction, again there would be mechanism for this reaction. So what are those mechanisms? Let's see. The first step is this 2NO undergoes a reversible reaction and form a product N2O2. In the next step, this N2O2 which is formed combines with hydrogen to give N2O plus H2O. In the third step, N2O which is formed combine with hydrogen once again to give N2 plus H2O. So these three steps are the mechanism for the complex reaction which I have written above. So these three steps are linked together for completion of that complex reaction. Among these three steps, the first step is fast step. This is the fast one. The next step is slow step, and then the next one is also the fast step. These are three steps in which the first step and the third step is fast and the middle step is slow step. Now again we know that the important step for us is the slow one, because it will help to find the rate of the reaction, and also we will write rate law using this slow step only. So let's write the rate law using the slow step. R is equal to K, product of concentration of reactant N2O2 H2 raised to some power. So this is the rate law which I have written using the slow step. Now let's note one thing over here. The rate law which I have written with the help of this slow step, the concentration of the reactant which I have mentioned in this rate law, this reactant is not present in the main equation. Let's go toward that main equation. This is the main equation. In this main equation, in reactant side, N2O2 is not present. Huh? N2O2 is not present in this main reaction. So from this rate law, now we have to eliminate this N2O2, because this N2O2 is not present in our main reaction, and those species which is not present in the main reaction is called as intermediate. It is intermediate. It is formed in the reaction but it is not present in our main reaction, so it should not be present in the rate law also. So another thing which is to be kept in mind is the rate law which we are writing should be free from intermediates. The rate law should not contain any of the intermediate. And what are intermediate? Intermediate are those which is not present in our main reaction. I have written the rate law over here with the help of this slow step, but this rate law is containing N2O2 which is not present in our main reaction, and so I have to eliminate it, because the rate law should not contain any such species which is not present in the main reaction. Now for removing this intermediate, we will take the help of this fast reversible step. The step which is fast and reversible one will help in removing this intermediate. So from that step which is fast and reversible one, this one, we will write the rate law once for the forward reaction, and since the reaction is reversible, so we will write another rate law for the backward reaction. So from fast reversible step, R is equal to K forward, and here for forward reaction, reactant is NO raised to the power 2. This 2 come from here, and another R is equal to K backward, and for backward reaction this would be taken as reactant N2O2, and power which will represent 1. This is first, this is second, both will be equal. Rate for forward reaction will be equal to backward reaction. So it will become like this. Kf NO2, sorry, NO raised to the power 2 will be equal to Kb N2O2. Now from this expression I have to find the value of this N2O2, because this N2O2 is the intermediate which we have to remove. So for finding its value, we will send this Kb toward another side. Kf by Kb equal to N2O2. Now I will put the value of N2O2 from here in that rate law expression. So this was our rate law expression, and this is the value of N2O2. So I will put the value of N2O2 from here in this place. So the rate law will become like this: R is equal to K. At the place of N2O2 I will write uh, sorry R equals to K. At the place of N2O2 it will be written as Kf by Kb NO square, and H2 will be copied at its own place. So this would be the final form in the rate law expression after putting the value of N2O2. Now if we want to remove this Kf by Kb, R is equal to K into, let it be K1 NO square H2. So this is the final expression for the rate law for the complex reaction, and this final expression is containing another constant K1, which is in the place of Kf by Kb. Kb. So once again I am going to recall some of the point for the complex reaction that is important to remember. Firstly, it will complete in multiple steps. Second, for a complex reaction, if we want to determine the rate, we have to look for the slowest step. Third one, if we want to know the rate of the reaction, for that also we have to look for the slowest step. While writing the rate law for the complex reaction, slowest step will help, but in the expression of rate law, intermediate should not be present. In this example, we have seen that if the intermediate comes in the expression of the rate law, we have to remove it. And how I have removed, I have also shown over here. Fast reversible step helped here to remove the unusual term, that is intermediate, so that our rate expression could be free of any of the intermediates. So these point should be kept in mind about the complex reaction.